Okay, let's take a look on an example of using the Gauss law to find the electric field due to a charge. Okay, so now let's say we have a charge Q located at the here at the origin over here. So we have a charge here, and we want to find an electric field. Okay, to find the electric field at a distance r from the origin due to the charge just now. Okay, so now we want to take uh, at a distance r from the origin. So this is the origin, so we take the radial direction. So let's take this point as r, and this point also will be r, and this point also will be r, and so as this point here, this point here, this point here, and if we take all the 3D of every point with distance r from the origin, we combine all that point, we can come to a closed surface of a sphere. Okay, so this is uh, our closed surface, which is in a shape of a spear, and the radius of this spear would be r, which is a distance from the origin or where we want to find the electric field. So here, and also at the surface over here, is our point of interest. What is the P at this point of interest? Okay, so here our closed surface over here is an imaginary point. Imaginary surface. Which we made up based on the our point of interest or where we want to find the electric field. Okay, so now the point charge Q just now is enclosed by a spherical surface, which is use the Gauss law, and let us solve this question to find the electric field due to the charge Q. Okay, so I will draw this a new figure over here. Okay, so we have y, x, and also z over here, and the charge is located here. Okay, this is Q. Okay, and okay, so the equation. The equation is the Gauss law. From the Gauss law, we already know that the integral, surface integral of the dot product or the electric flux that is going through a surface, differential surface area, is equal to the charge enclosed within that closed surface over epsilon. So here we will use epsilon 0. Okay, so here we have to solve this part, and also later on we will solve this part. Okay, so now we have the Q over here. So it doesn't stated that the Q is either a positive charge or a negative charge. So we just assume that it is a positive charge. And we already know that a positive charge is a source of the electric field, meaning that we will have electric field radiating from the charge. Okay, so please imagine this in 3D, and here we can express this electric field. Okay, the vector can be expressed as the electric field, the magnitude, and the direction, which is in r direction. Okay, so that is for the electric field. Okay, later on we will have to use this information and substitute it to the equation, the Gauss law equation. Okay, so now for the, okay, so we already done with this one, this part, the electric field. Now we have to know the vector for this differential surface area of the closed surface. Okay, so now I pick this particular area as the ds. So the magnitude is as it is, we just write it as it is, ds. And the direction is given by the 90 degrees from the surface. So here this is, what direction is this? This is also in r direction. Okay, so now we can use these two information, and for the left side of the equation, we have E, the magnitude in r direction, dot product with, okay, ds, also in r direction. Okay, so how about the charge enclosed? So here, let's go back to the definition. The charge enclosed here means that the charge which is enclosed in this closed surface. So in our case, our closed surface is a sphere like this. So the charge that we have inside this closed surface is this Q. Okay, so we only have that one. So we just write it as Q. And then, okay, so now what we do is solve this dot product. So here we have okay, R dot R. So E D S. So we have the integral there. Okay, so the dot product between two same vector, so in this case R and R, will equal to 1. Okay, so here okay, if you want me to just a note, let me write it here. Okay, the magnitude, which is 1, cos. So this is cos 0 because it is parallel to each other. So this is 1, this is 1, this is 1. So we have here 1. Okay, okay. Let's go back to the calculation over here. We have E ds is equal to Q epsilon 0. Okay, so here, okay, okay. So here I will rearrange. Okay, so here we have we put the electric field outside. So here we have the integral of ds. Okay, so integral of ds will give you surface area. So here, surface area, our closed surface is now a sphere with radius r. So here, E integral of dx is equal to surface area of a sphere, r squared, equal to Q epsilon 0. And we rearrange this. So, because we just want the electric field, 4 pi epsilon 0 r squared. Okay, so that is the magnitude of the electric field. So as for the vector, we already know just now that it is a positive charge, so the direction is radiating from the charge itself. So as for the vector of the electric field, we can give the direction as R. Okay, sorry, you cannot see that. Okay, so here in vector we have E, electric field at any point, at any point which is a distance r from the origin, or any point on the closed surface is equal to q for over 4 pi epsilon 0. So this is epsilon 0 r square in r direction. And if you compare, this is also similar to the one that we already derived using the Coulomb's law. Notes on using the Gauss law to solve the electric field. Okay, so here, as you can see from the example, Gauss law is easier to apply compared to Coulomb's law, but you can only use this to a limited to symmetrical charge distribution. And to successfully apply the Gauss law, the surface S should be chosen so that from symmetry consideration, the electric field, the direction is normal or tangential to the each of the ds, okay, each of the subsurface of S.